We're going to keep going with this one. Find a series for 7 sine squared of x. Now, I'm sure that you were like I was back when you covered trig identities. You're like, where am I going to use this stuff? Well, here's a good place. Sine squared is 1 minus cosine of 2x. So we can use this identity because this is a known series for cosine of 2x. We can plug in 2x into that known series. Just as a reminder, cosine of x has this series, the sum from n equals 0 to infinity of -1 to the n, x to the 2n over 2n factorial. So you plug 2x in there and make some headway. So for the rest of that, I'm going to get a little bit lazy here. This one's already done here for us. But let's talk through it. So you got 7 times that trig identity, which was 1/2 cosine or 1 minus cosine of 2x. And let's take and plug the 2x, this part right here, into our series for the cosine. So we did that right there. And then let's play around a little bit as well. What we can do is notice that the first term in this series is actually going to be a 1. So if you look right now the series starts at 0. But when I put in a 0 for n, that's to the 0 power, this is to the 0 power, 2 times 0 is 0, 0 factorial is 1. All of this is going to be a 1. So what we can do kind of sneakily is factor out that 1, and now that 1 and this 1 are going to cancel. This leaves me with a negative out in front. Okay. We got the 7/2, the 2 1s are going to cancel out. And now we're going to do something else kind of sneaky. Let's do it here in green. This is like a -1. So how can I get rid of that? Well, I can bring it inside the parentheses, and instead of a negative and then -1 to the n, I can make that -1 to the n plus 1. So, okay. And then what? We got the 2n factorial. Oh, last but not least, this part right here, I've got a 2 here. I can get rid of that by canceling out one of the 2's here with one of the 2's here. Now, when you're dividing things, you subtract their exponents. So 2n minus 1 from this one here, and that's how come I end up with the 2n minus 1 here for my exponent. So a little bit of fancy footwork here with canceling and shuffling things around, but you get a nice series for this. And if you apply the ratio test, you find it has a radius of convergence of infinity. So the ratio test would end up to be 0, and our radius of convergence would be infinite. So nice. So a nice little use for your series here. Any comments on that one? We're going to keep working through some of these examples on your handout. So example I, again, this is one I'll do in OneNote, but let me write it down here. Limit as x approaches 0 of 1 minus cosine of 4x over 1 plus 4x minus e to the 4x. Now, personally, if I was stuck doing this, I think I'd be using L'Hopital's rule. All right, but there was a problem in WebAssign that asked you to do this using series. Now let me just show you how it's done using series. So here you go. So 1 minus the series for cosine of 4x. And what they've done is they've expanded that here so they didn't just write it in series notation. And likewise, they took and expanded the series for e to the 4x. And that series is right here. Now, both of these terms in the numerator and denominator will simplify. If you distribute that, that negative to every term in the numerator, you'll get what's below here. The negative is going to change the sign. The -1 and +1 will cancel. And likewise, similar phenomenon is going to happen in the denominator. Now, if you look at these two terms, there's not much of a difference between these, but that's okay. We're going to look at the limit as x approaches 0. Before you take that limit, there's a common factor of an x squared that can be factored out. So, okay, we'll factor out the x squared, that term right there. The x squared is going to leave behind a 4 squared, or 16 over 2 factorial. The x squareds in the numerator will cancel with an x squared in the denominator and give us something like this. Now, the cool thing is that you're taking the limit as x approaches 0. So all these other terms here are going to disappear. All these terms here have an x squared. They're going to disappear. These have an x or x squared or more. They're going to disappear. And so finally, you're just left with a simple little ratio, and that ratio turns into -1. But just so you know, these last two are examples of things that I didn't put in your homework. There's a lot of problems that I avoid just because there's parts about it that I don't like. But I do want you to see some of the things you can do with series, which is why I gave you your handout and why we're covering these things not kind of live, but in a narrated fashion. We will get back to doing some of these things more by hand with the last two examples, but I got one more example to do first. Before I do that one, any questions about example I here? All right. So let's take a look at example J. So find a series, or at least the first few terms in the series x over sine of x. Now, if it was the other way around, it'd be pretty easy. But this way is kind of a pain. In fact, it's a real pain. You got to do it by long division. So what's that going to look like? So here it is by long division. You've got your x in the numerator right here, divided by the series for sine of x. And here we've written out 3 factorial is 6, 5 factorial is 120, etc. We're going to divide that into the x, and it's just some tedious work with long division. And here's the first couple terms, which in the problem that I did for you here is all that we need is the first few terms. But you can get as many as you'd like. It's just not that fun. It's really not. All right. Well, let's get back to one that is a little bit more relevant to your homework. And we'll call that one example K. Now, if you've been relaxing for just a minute, hopefully not nodding off, but maybe just relaxing, now's the time to pick up the pen and start again. They want you to sum this series. Wow, really? Well, we don't know what x is. That's okay. They still want to sum this series. Now, from my point of view, what I would do is I'd notice that, first of all, these are all to the n power, or something to the n power. So let me rewrite those maybe together a little bit more. For instance, we'll take care of the -1 in just a minute. -1 to the n. I can think of this as 4 times x to the 6, both to the n power, right? Because if I remove the parentheses, this multiplies each of the exponents on the inside. So I'd have 4 to the n, x to the 6 to the 6n. And you know what? Playing that same game, I can sneak this -1 inside here as well. So I finally get n equals 0 to infinity of -4 x to the 6 raised to the n over n factorial. And this is supposed to be the aha moment. The only reason it's not is because we haven't worked with these things enough that you're going to recognize these series right off the bat. So let me remind you of some of the more common Taylor series. That's this list right here. Can you see that this fits the pattern of one of these series? I'll let you take a look at this and then look at look back here.
E to the x?
Yeah, it kind of looks like e to the x. Let's just double check it here, right? So you've got, you know, something to, you know, the nth power over n factorial. And that's kind of what we had here. In fact, it looks like you've taken this term right here, -4x to the 6, and dropped it in your series for e to the x. So a compact way to write this expression then would be e to the -4x to the 6. That's your series. So we kind of reverse engineered it that way. Okay. How are we looking on example K there? All right, so look out for something like that in your homework. And the next example we're going to do kind of one of my favorites. It's to approximate integral with just a few fractions. So let me pull that up. That'll be example L. Wow. Got a lot of examples for us in this section. So let me get that one up here for us. Use a series to approximate the interval from 0 to 1 of 4x cosine of x squared dx. And let's see how many digits to within 0.0001, 1/10,000th. So I claim we can do that with just a few fractions, like 4 fractions. Should be able to do it for us. What do you think? Can I do it with 4 fractions? Oh man, rats. Oh, come on.
can do it.
Ah, I was trying to play the Mission Impossible theme, but all right. Great, YouTube gave me an ad. My bad. Let's just go back to this. Of course, your view never changed. That's all right. So what we're going to do here is we're going to do this with series. Let's start out with the reminder. Cosine of x is the sum from n equals 0 to infinity of -1 to the n over 2n factorial times x to the 2n. And then I want to figure out what cosine of x squared is. -1 to the n over 2n factorial x, actually not x. Let's see. No, not quite x. So it's going to be x squared in here. And that's going to put an x squared in here. And that's going to be raised to the 2n. So let's simplify this a little bit. That's going to be the sum from n equals 0 to infinity of -1 to the n over 2n factorial x to the 4n. Now I want to come up with the complete function there. I want 4x times cosine of x squared, which is going to be 4x times this series, sum from n equals 0 to infinity, -1 to the n over 2n factorial x to the 4n. And here's where I want to take that x and put it on the inside. So it's going to be 4 times the sum from n equals 0 to infinity of -1 to the n over 2n factorial x to the 4n plus 1. Great. So now I've got a series representation for this function, and I'm going to integrate it. We're okay with how I got this series here? Now, let's do the integral. 0 to 1 of 4x cosine of x squared dx is going to be the integral from 0 to 1 of 4 times the sum from n equals 0 to infinity of -1 to the n over 2n factorial x to the n, x to the 4n plus 1 dx. Now, a lot of this has nothing to do with x, so we can factor that out. So that would become, actually, you know what? I don't want to put the integral there. I gotta move that integral in. So that integral is going to go all the way in here. So it's going to be 4 times the sum from n equals 0 to infinity of -1 to the n over 2n factorial times the integral from 0 to 1 of x to the 4n plus 1 dx. And this, I'm hoping, is something that we can integrate. That's just a little old polynomial term. Okay. So what's that equal? The sum from n equals 0 to infinity of -1 to the n over 2n factorial. The antiderivative of that is going to be x to the 4n plus 2, add 1 to the exponent, divide by the same exponent, 4n plus 2, evaluated between 0 and 1. I'll just kind of put a little bracket around that as well. So now you got to plug in the limits of 0 to 1. You can see how kind your instructor was because at least one of them is 0, right? And plugging in a 1 is not going to be that bad. It's just going to be 1 over 4n plus 2 minus 0. So let's take a look. That's going to be 4 times the sum from n equals 0 to infinity of negative 1 to the n over 2n factorial times 1 over 4n plus 2 minus 0. And of course, I don't need the minus 0 there. I can just write this like without it. So 4 times the sum from n equals 0 to infinity, negative 1 to the n over 2n factorial times 4n plus 2. Okay. Now, keep in mind, my goal is to try and approximate this integral. And I want to approximate it to within 1/10,000th. There's something very nice about this series that'll help me do that approximation. Does anyone see what's helpful about this series that'll help me in my approximation? Anyone? What does this series do that'll help make finding an approximate value a lot easier than it could be otherwise?
Converges?
Well, it does converge, which is nice. It alternates. So the series alternates. So that's pretty cool. Let's see. Now, what does the alternating part mean for us? Why do we care? If the series alternates, the error, R sub n, is going to be S minus S sub n, sum of the first so many terms, and that's going to be less than or equal to the first term you leave off. So that's pretty nice. So what we want to do is write out a few of these terms until we get to one that is small enough that we can just say, all right, let's leave that off. Okay? So that's the game plan with these type of problems. This is exactly what you can expect from me on an exam. It is to do one like this where you have to approximate something. Okay. Now, let's expand this. Now that's kind of a chore here with these ugly terms. You got 2n factorial and then 4n plus 2. I mean, maybe at n equals 0, it's not so bad because you get 1 times 2. All right, so that's not so bad. Let's take a look. So the first one would be a positive 1 over 2. Second one's going to be negative something, but it's a little bit of a pain after that to work with these things. So let me make a suggestion here. Let's take out our calculators and get our calculators to help. Now you can do this in a couple of different ways. So let me clear up this stuff here. I'll clear out that. Yeah, and let's see. Let's clear out this stuff here. Now my calculator happens to be in sequential mode still. Doesn't matter if you use sequential mode or not, but let's put in, I'm not going to worry about the -1 stuff. You could put it in if you want, -1 raised to the nth power. That's fine, doesn't matter, because we're not really going to be worried about the sign of this term. We're just worried about how big it is. Divided by. Now you need parentheses, 2 of them. First term you're going to have is 2n, parenthesis, and then you need the factorial. So the factorial you can find underneath the math key, math, and go over to probability, and it's the 4th one down. And then left parenthesis, 4n plus 2. Right parenthesis again. The first one closes off your binomial, the second closes off the denominator. And I'm also going to enter v sub n. I'm also going to enter another one just to help you out a little bit so we can see things a little bit better. Because what this is going to do is going to give me a decimal value. I'm just going to see how small this is getting, and it's going to help me figure out how many terms I can ditch, or what term I can start ditching the rest of the series. But it's hard to tell what the numbers actually are. So let's just do this. 2n factorial. So order probability again, 4th option down. And then 4n plus 2. And this is literally what I did when I wrote out my notes. So, okay. Hopefully you've kept up with these 2 things that I've entered in here. You can see some of my keystrokes here. So I'll scroll through them a little bit. Let me see if I can pull those up. There. So there's all the keystrokes that I used to put in these 2 things. Let's check our window. Independence should be set to ask. Go over to table. And let's just delete a few things so we can start fresh. We'll start with 1, 2, 3, 4. I wonder if I got an error with 1. I'm not sure where I got an error with 1. Oh, that's just one of my settings. It shouldn't be affecting you. All right, and that should be good enough to stop. The first term I can leave off is the one that's going to give me a number less than 1/10,000th. So this isn't quite there. If I look at this 3rd term here, well, oh, it's right on the borderline. So we can go an extra 1 right here. So this is the first term I can leave off. But it's hard to know what these things are, which is why I wrote this other series. So the fractions we get are going to be 1/2 is our first one. 1/240 is the second one. 1/10,080 is the third one. 1/725,760 is the next one. So the nice thing about the second way I wrote that is you can actually see these terms and see the fractions that we need. So let me copy those down into a series. 1/12 plus 1/240. So it looks like this. So the first term I can leave off is really this one, because this will be a little bit less than 10,000, which means my error is less than 1/10,000th, which is what I wanted. So if I just use those first three to come up with my estimate, I get 1.6833 bar, which isn't too bad. If I use the first four terms, then I get even more accuracy. Then I get 1.68293. So with just four fractions, I'm getting some pretty good accuracy. Now I'm going to put, I think I already did put another Desmos link in the chat. Let me put it there again, in case you didn't get it the first time. Chat. Okay, so if you want it, it's in the chat. If not, no big deal. So here's our series right there. Here's the actual function. Let's compare the two. Now, as I add more terms to this series, I get a better and better approximation. Now, if I wanted the exact value of that series, here it is in Desmos, 1.6829419, et cetera, et cetera, et cetera. But okay. Let's see, let me zoom down here. And we'll take A back to 1. If I just use one term, actually, I guess that'd be two terms because I get 0 and 1. Two terms, yeah, not too bad. At least I get the first 10th right. Two terms. So you can compare this one up here with this one down here. Two terms, pretty good. Three terms, look at this. I think like 5 or 6 terms. Look at 5 terms, I've got 10 digits of accuracy. At 6 terms, I got a full 11 digits of accuracy. That's amazing. So with 6 of the correct fraction, you can get 11 digits of accuracy out of this expression. That's pretty amazing. Okay. That one was a longer example, but an important one. So if there's something that I was unclear about, let me know. We'll take a look back at it. Maybe something went through a little bit quickly. Is there anyone out there?
Yeah.
Yes, one person. All right, thank you. Maybe it's a good time to take attendance right here, right? All right. Let me pause things here. In fact, we'll stop things here. Last chance. Any comments or thoughts? Okay,